So humans rely on sensors to monitor and code the external world. But this guy to stand here on this high line, he's got to use his visual system, his vestibular system, and his proprioception to help him balance. With his visual system, he can sense velocity through the movement of images across his eye. With the vestibular system, he has semicircular canals in his otoliths. So his canals will allow him to sense angular acceleration and his otoliths linear acceleration. With proprioception, he's got pressure cues on his feet, muscle tension changes, things like that. So how does the brain integrate all this information? In particular, with optokinetic input, how does the posture respond to this? So in the world, as you can see in this video, the body leans over very slowly. And so we want to know what captures these dynamics. We want to answer these two questions. With visual input, why does the body tilt with slow dynamics? And how does the central nervous system integrate the information? I'm going to try to answer now with the semicircular canals and the state estimator model. We'll go into that soon. So your visual system, your canals, and we're going to lump your otoliths and your proprioception together in something which is called the tilt sensors. So if you had a head velocity input, let's say a step, your eyes would just measure that as retinal slip. Your canals have a cupula in them, so they would sense a high-pass filtered velocity. And your tilt sensors, let's just assume they integrate and they give you a measure of tilt. So we can assume your visual system has a direct feed-through, your semicircular canals are like a high-pass filter, and your tilt sensors integrate. And so you can take these measurements, and you can feed those same measurements into your central nervous system. And then it processes it and gives you an estimate of tilt, which, as you've seen before, is slowly tilting over. So we're interested in what happens with visual input and posture output. And if you look at the cupula dynamics, it takes care of the high-pass filtered stuff. So you need to compensate for that. So in order to estimate tilt in any sort of situation, you need some sort of low-pass filter in order to process the information. So we expect a low-pass filter if we were to look from visual input to postural output. And so even without direct stimulation, the canals affect postural response during optokinetic input. So how can we integrate this sensory information? We expect a low-pass filter, but let's just say we have 3 sensors. We want to know what the estimate of tilt is. We're just going to invert them so we get our units back, weight them in some sort of way, and then add them together and then integrate to an estimate of tilt. Well, there's some problems with this. How do you know you can invert the sensors? Will this be stable? How do you choose the weightings? And also, what are the cross-couplings between the different sensors and their dynamics? And how do you know what your estimate of tilt will be? So we think this is not the way to go, and perhaps is to use a state estimator. So a state estimator will do a near inversion of these dynamics, choose weightings based on the noise covariance, and minimize the error. And so without going into much detail, I'm going to show you the results. So if you were to feed a step input into the estimator model and look at tilt, you would have a tilt output that slowly tilts over and then stays, just like we saw in the video. And if you were to look at the tilt domain response, so this red is the subject tilt, and the yellow is the model. And in this, we added a habituation time constant. So when people have repeated stimuli, they get used to it, and so they don't react as much anymore. So we added this time constant to our model, but you can see the model and the head tilt are pretty comparable. And another way we can look at this is look at the frequency domain. So the axis is visual perturbation frequency, so different frequencies that we can perturb people sinusoidally. And the y-axis is the posture response ratio, the ratio of the posture response over the input velocity. And it's the magnitude in dB. And so again, the yellow is the estimator model, and we still have the habituation time constant in this. And the dots are the human responses. And so the estimator is able to capture the dynamics of people during visual perturbation. And so it compares reasonably well with what humans do. So in conclusion, processing the vision accounts for canal dynamics. And these dynamics cause low-pass filter behavior, as you can see in humans and in the model. And so we think the central nervous system behaves like a state estimator. And I'll leave you with dots spinning are all I can see. Semicircular now disagree. It's not just the weight. a low pass compensates. My lean estimate is as good as can be. Thank you.
Any questions for a speaker?
So, you're perturbing the visual information, but the vestibular and proprioceptive information aren't being changed.
Correct.
So, do you expect that at some point people will sort of learn that their vision is no longer a reliable source and then go back to the standard, or do they just stay focused at that point?
Perhaps, but after a long while. So, like our experiment's about 2 hours long and they still don't learn. They just can't help but tilt over. But I can see maybe for like a long time, like if you were to, I guess similar to when you would wear glasses that are inverted and you get used to it and your brain like sorts itself out and gets used to that, I would see that they maybe come back.
Because the tilt, when you're getting more loading on one leg than the other,
Right.
shouldn't that be an indication that you're doing something wrong?
Not wrong, but that you're, I guess most subjects feel that they don't realize they're tilting until they feel their proprioceptors are telling them they're tilting, and then they sort of stop at that point.
I actually have one. Oh, sorry. Go.
Okay.
I'm wondering, do people blindfolded just ask balance? Do they find some able to compete it, or do they proceed to vertical?
People blindfolded? I would say they would keep to vertical, because in this case we're disturbing the visual input, so they're trying to remain upright, but they can't. But I think if we blindfold them, we're not disturbing them anyway, they just don't have that information, or they don't trust it as much.
You said they try to remain upright, but they can't. Is the subject, how much is the subject instructed? In other words, do you just tell them this is going to move, do whatever you want to do, or tell us a little more about your study?
I guess we try not to give them any sort of indication of what to do. We just say, just stare at the screen, do what you naturally do, and then we just see what they do. So we don't tell them to like where to look or anything, but we do rotate the dots above their head, and they just tilt over.
Does anybody get bored and close their eyes?
No, well, we were worried about the boredom, so it was a pretty long experiment. So we actually play an audiobook so they would sort of keep awake. But it's a lot of standing, but yeah, they just always tilt over.